As we have discussed in the last class, in the one-way ANOVA procedure, we compare variation among sample means with the variation within samples. So in this class, we first consider how to calculate variation among sample means, variation within samples, and how to derive the test statistics to test whether there is difference between population means. We first consider a measure of variation among sample means. Variation among sample means. A measure of variation among sample means. This is what we first consider, a measure of variation among sample means. Remember this, in the hypothesis test for two population means, we measure variation between two sample means by calculating the difference x bar 1 minus x bar 2. To compare two population means, we measure variation between two sample means by calculating their difference x bar 1 minus x bar 2. When more than two populations are involved, we cannot measure variation among sample means by taking the difference. If we have three population means, we cannot calculate variation among sample means by taking the difference between these three samples. Sample means x bar 1 minus x bar 2 minus x bar 2. This is meaningless. We cannot take such a variation. However, we can measure that variation by computing the standard deviation or variance of sample means. If there are more than two means, we can compute the variation among the sample means by computing the standard deviation or variance of sample means. Standard deviation of sample means. We can calculate the variation among sample means by calculating the variance or standard deviation of sample means. We cannot take the variation among the sample means by taking the difference between sample means when more than two means are involved. And in one-way ANOVA, we measure variation among sample means by a weighted average of their squared deviations about mean x bar of all sample data. In one-way ANOVA, we measure the variation among sample means. Variation among sample means by weighted average of their squared deviations about weighted average of squared deviations about mean x bar of all sample data. That is the overall x bar. A weighted average of squared deviations, say x bar 1 minus x bar square, weighted by, say, I will explain what is the weight, and we take all these squared deviations of all the populations from the mean of the entire population. The weights are the sample sizes, that is another thing which we will see. And that measure of variation is called treatment mean square. This measure of variation is known as treatment mean square, MSTR, treatment mean square. Treatment mean square and is defined as MSTR is defined as treatment mean square is equal to SS treated by sum. SSTR means treatment sum of squares, SSTR divided by k minus 1 degrees of freedom. K is the number of the number of populations or the number of means. If we have 4 populations, K is 4, K minus 1, etc. So MSTR is equal to SSTR by K minus 1. K is the number of populations sampled and SSTR is equal to N1 into x bar 1 minus x bar square plus N2 into x bar 2 minus x bar square plus etc. Nk into x bar k minus x bar square. SSTR is calculated using this formula, where k is the number of populations sampled. As you can see, x bar is the common mean for the entire population samples. N1 is the sample size of the first population, N2 of the second, Nk of the third. X bar 1 is the mean, sample mean of the first population, x bar 2 sample mean of the second, x bar k sample mean of the kth population, and x bar is the overall mean. And we call this treatment sum of squares. MSTR is treatment mean square. Treatment mean square, treatment sum of squares, MSTR. And so MSTR is SSTR divided by its degrees of freedom. And MSTR is similar to sample variance of sample means. Actually, it is the sample variance of sample means. Sample variance of sample means. If you think of, say, 100 means, and if this N1, N2, etc., Nk are ignorant, take this x bar 1 minus x bar square plus etc. divided by k minus 1. Remember this? Here k is the number of sample means, n minus 1, k minus 1, because we have k sample points. Here the sample points are sample means. Now the difference is, so this is nothing but sample variance of sample means. And if all sample sizes are equal, MSTR is equal to common sample size times sample variance of sample means. If N1 is equal to N2 is equal to, say, Nk is equal to N, this N can be taken out. Then we will get a sigma Nj, or we can take this N out, and this becomes N into what is known as the sample variance of sample means. So this MSTR is nothing but the sample variance of sample means. If n is equal, it is nothing but the common sample size, n multiplied by sample variance of sample means. This is variation among sample means. MSTR is variation among sample means. Now we consider variation within samples. Variation within samples. We consider variation within samples. Now, this measure is the pooled estimate of the common population variance sigma square. Variation within samples is nothing but the pooled estimate of common population variance sigma square, and it is called error means of square. Error means of square, MSE. Error means of square. Treatment means square. Treatment sum of squares. This is error means square, MSE. Error means square, MSE, and it is equal to SSE. Error sum of squares divided by degrees of freedom n minus k. SSE by n minus k. N is the total number of observations, and this SSE is equal to calculated by n1 minus 1 into s1 square plus n2 minus 1 into s2 square plus nk minus 1 into sk square. That is SSE, n total number of observations, and SSE is error sum of squares, calculated as actually n1 minus 1, this is sigma x, this is sigma x minus x bar square divided by n minus 1 or n minus 1 divided by nk. You will get what is known as the pooled estimate of the common population variance, SSE. So MSE is equal to SSE by n minus k. And so we have MSTR and MSE. Now finally, what we require is how to compare variation among sample means MSTR with the variation within samples. How to compare variation among sample means MSTR to variation within samples MSE. To do this, we calculate what is known as the statistics F is equal to MSTR by MSE. To compare variation among sample means with the variation within samples, we use the statistics F is equal to MSTR by MSE. We refer to this quantity the F statistics. This quantity is referred to as F statistics. If the value of F is very large, then we will say that variation among sample means is much larger than variation within, and it is evidence against H0. That is, variation among sample means much, that is, variation between sample means much larger than variation within samples, evidence against H0. Or if the value of F is small, that is, MSTR is not much different from MSE, null hypothesis will not be rejected. So this is the idea behind one-way ANOVA. We calculate MSTR, MSE, the ratio is F, and its distribution will be considered in the next class, and a decision is taken. Now let us consider an example. In the United States, data is collected about household energy consumption and expenditure on energy, and we want to determine whether a difference exists between mean annual energy consumption among US households in Northeast, Midwest, Southwest. The population is having 4 categories: 15, 10, 13, 14, 13, mean is 13, 17, 12, 18, 13, 15, 12, 14.5, 11, 7, 9, 13, 10, 10, 12, 8, 7, 9, 9.2. Our H0 is mu1 is equal to mu2 is equal to mu3 is equal to mu4. H1 is not all these means are equal. Now we have MSTR first. We have k is equal to 4, n1 is equal to 5, n2 is equal to 6, n3 is equal to 4, n4 is equal to 5, x bar 1, 13, x bar 2, 14.5, x bar 3, 10, x bar 4, 9.2. And the overall x bar is equal to 11.9. 11.9. And applying these values, you will get MSTR as equal to 32.5. 32.5. And to determine MSE, S1 square is 3.5, S2 square is 6.7, S3 square is 6.6, S4 square is equal to 3.7. Applying, we will get a MSE as equal to 5.144 and F is equal to MSTR by MSE is equal to 32.5 divided by 5.144 is equal to 6.32. And this S1 square is the variance of the first population, variance of the second, variance of the third, variance of the fourth. For calculation, we have easy to calculate formulas, but in the age of many statistical softwares, we will not calculate any of these quantities manually. Now the question is whether the value of f is large enough to conclude that H0 is not true or H0 is false. And to answer this question, we have to specify the distribution of f. To answer this question, we have to specify the distribution of f. That we will see in the next class. So remember this. What we do is we compare variation between means with the variation within means, or between sample means and variation within each mean, and we compare this. And the test statistics is a comparison of these variation between sample means with the variation within samples. Variation within samples. If variation between means is much larger than variation within samples, within populations or within samples, we reject H0. To take a decision, we have to find out, or we have to specify the distribution of f, and that is what we will consider in the next class.